Kesavan, shall we start? Anyway, I'll take a couple of minutes to introduce you. So by that time, I think some more participants will join.
Yes, Subbu, we can start.
Yes, thank you, Dr. Kesavan. Thank you. So good morning to all. So we are second day of the workshop. In the first day, yesterday, we had three sessions. In the first session, Dr. C.P. Paul covered like introduction to additive manufacturing. He covered basics of the processes and then to the a state of the art what people are working on in additive manufacturing and which direction we're supposed to go. So those things is covered in this lecture. After that, I gave a session on additive manufacturing technique. There I covered 7 basic processes. I just went to little more depth. Whereas in the last session, this is given by Dr. Lakshmi Narayanan from IIT Delhi. So he has covered not only the processes, along with that, if you process the different materials like metals and alloys. So what are the challenges are there? How to address that? So if you find the challenge, how to connect with the basics. So he gave the way for how to do a research also in that. Okay, so in line with that, today we'll start our first session on design for additive manufacturing. So if you will make a product for your need in general, okay, but apart from that, requirement of that particular product in a particular shape and dimension, what we're supposed to do based on the process, something should be changed on the product, dimension, geometry, or shape, whatever. So for each process, we're supposed to consider that how to design a particular product or a part for a particular process event. So in that case, for additive manufacturing also, there are certain rules and regulations for how to design a particular part for this particular process. So in that case, we're supposed to know about design for additive manufacturing. Today as a first speaker, Dr. Kesavan will deliver a talk on that. So I'm happy to introduce my colleague, Dr. Kesavan. So he has done his diploma in TPEVR Government Polytechnic Vellore in 2000. After that, he has joined for BE in Madras University and completed in 2003. After that, he has done his ME in Metallurgical Engineering from Anna University and then completed in 2006. And then he has done his PhD from IIT Madras in Metallurgical and Material Engineering and then graduated in 2011. Apart from that, he has have research experience also. It is a little bit wide because after his BE, he has worked as a engineer, senior engineer in R&D Tribology section, National Bearing Jaipur. After his MTech, he has joined as a research engineer in a GE from 2012 to 2017. After that, he will become a promoted to lead engineer from 2017 to July 2017. Then he has joined as assistant professor in IIT Palakkad 2017. He secured many awards and honors. He is a recipient of Institution Silver Medal for the best PhD thesis from IIT Madras, Chennai. And he is also a recipient of above and beyond awards from GE Global Research. And he secured GE Certified Six Sigma Green Belt from GE DMAIC Council. In his account, he has 10 journal publications. And then he is having 5 patents and 2 trade secrets. This is a short introduction. I request Dr. Kesavan address the participants on the topic design for additive manufacturing. Over to Dr. Kesavan.
Thank you, Dr. Subbu, for your nice introduction. I hope my voice is audible and my screen is visible to all of you.
Yes.
Okay. So for the topic for today's presentations, I've chosen the topic design for additive manufacturing. For about next 1 or 1.5 hours, I'll be talking on that topic, DFAM. Before introducing DFAM, I would like to briefly discuss about the process additive manufacturing. Why additive manufacturing? What are the some advantages or challenges that are currently faced in additive manufacturing in globally from industry point of view and also from academics and all those things. What you are seeing on the right hand side is a laser powder bed fusion technology that is a 3D metal printer which is available at IIT Palakkad. So to start with, so in my presentations, I'll be covering so I'll be starting actually additive manufacturing. Before that, I just wanted to give a brief introduction about manufacturing processes, which you already aware of, which some of the processes you already aware. Let me start with the classification of manufacturing processes. So you all know that there is a traditional process and non-traditional processes. Traditional processes are, you all know, actually it is given here, and the additive manufacturing that comes under non-traditional manufacturing processes. And you can find there are several such processes are available. So I'm going to briefly discuss about what it is. When you compare the conventional manufacturing processes, which we generally call top-down process. So if you look at the conventional process, subtractive, so you'll be removing or start removing the material from the surface, and finally you end up with the final component. In this process, you may end up with a large loss of material. Whereas when you compare that with additive, it is the right opposite. Additive is a bottom to top process. So you are starting making the component with the single layer or the first layer. From there, actually, you are printing the component. So it is right opposite to subtractive. So the additive is called bottom to top process, whereas the subtractive is called the top to down process. So this is the basic difference between additive and the subtractive, or I would say conventional and unconventional in terms of manufacturing particular component. Okay, so coming to the definitions, as I mentioned, I may be repeating some of the terminologies, some of the concepts. Please bear with me. So as per ASTM, the additive manufacturing is a new process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodology. So now you know what is subtractive, what is additive now. If you look at in detail, you can make a component, or before making a component, you have to start with developing or making a CAD model, 3D CAD model. Then there are several processes involved before you start manufacturing it, or before you make the component. So those processes like slicing, layer-wise assembly, and optimization, and several other processes, which we are going to discuss in coming slides. So in additive manufacturing, what you see on the computer is what you are going to exactly get after the printing. So it's called what you see is what you going to get. So this is the additive manufacturing. If you look at the additively manufactured component, so example, if you take here, it is an impeller. If I look at the microstructure at very high magnifications, you can see there is a beads, right? So every component, the complete component is made up of single layers. It's assembly of layers, you can see. So this is how the component is assembled. So you actually finally end up getting the component. If I compare this scenario with the welding, which you are seeing on the right hand side, even if you take the welding process, so welding also you are actually developing a component, or you are joining a component or materials by layer. So basically you are introducing the different beads. So those beads are helping to join the materials. So finally, you end up actually making a component, or you are joining the component. So in this case, can you term welding as additive manufacturing process? So if you look at the wire arc additive manufacturing process, that operates in the same principle. So there you end up making a component by layer on layer construction. So you can call that process also like additive manufacturing process. So this is the basic difference between metal additive and welding. So you can make a component by welding process, that process called wire arc additive, or there are other processes also. Even by using solid state process like friction based welding processes, one can make a component. Even that process also called as a additive manufacturing processes, right? So AM classifications, I believe Dr. Subbu would have briefed on all these processes. I'm just giving a glimpse of it. So there are 7 different processes available, starting from VAT polymerization to direct energy deposition. You can see the way they are arranged. So VAT polymerization is the process which consumes very low energy. So basically the energy spent to make a component is very low. As you go to high, as you go from VAT polymerization to other processes, you see the energy spent is more. Okay, so the highest energy is spent for the process called direct energy deposition. This is also called as a lens process. So the powder bed fusion process is the next lowest, the next second highest energy density process, in which SLS, SLM, DMLS, and all those processes are actually classified. So as far as metal components are concerned, so if you want to make any metallic component, let's say from powder or from solid wires, such that you have to actually use high energy process. So at least like in a powder bed fusion or direct energy deposition fusion processes. So this is how the AM is classified. Okay, so there are some unique capabilities of additive manufacturing. The first and foremost unique capability is hierarchical complexity, which you cannot think of making or introducing this with the conventional manufacturing process. And second is materials and shape complexity. And the third is functional complexity. I'll explain that with the simple examples. If you look at some of the components, the printed components, these all the components, they are manufactured by additive. So if you look at the first component, it is an impeller. So the impeller has hierarchical complexity. And if you take even the last example is it's basically a die. This also has some hierarchical complex. What I mean by hierarchical complex is that if you go from surface to core, the manufacturing complexity is increased. So it is not that easy to manufacture such complexity by using conventional manufacturing methods. So that's what we call that as a hierarchical complexity. So materials and shape complexity. So any shape, for example, if you take the third example, so here it is a shape complexity. Such a shape, in order to make such a shape, it is very difficult by conventional. At least you need a 6-axis machine to make such a complex, and of course it will be very much challenging. So this is the shape complexity and functional complexity. So for the functional complexity, I'll again quote the die component. You see here, in order to meet the functional, so it has a different complex parts at the interior. So making such a complex cooling channels, it's called conformal cooling channels. So to make such a conformal cooling channels, it would be very difficult by conventional manufacturing process. So these are all we can classify under unique capabilities of additive manufacturing. So so that are possible only by additive manufacturing methods, right? So if you take the technologies currently, there are actually several technologies. They are called disruptive technologies. Example, automation and the energy storage, renewable, mobile internet. This all disruptive technologies at present. Even the 3D printing is classified as a disruptive technology. So disruptive is something completely changed the world. So example, so the smartphones now it has changed. So you don't have to go to a bank to transfer the money, right? So you have to just go to bank to create your account. That's also rest all banking you can do by sitting at home by using your mobile. So that mobile internet is called a disruptive. So that made disruptive. So similarly, this 3D printing also made disruptive in manufacturing scenario or manufacturing world, because now by sitting at your desk, you can actually design and make a component by just connecting the world. So that's the reason it is 3D printing also called as a disruptive technology or classified under disruptive technologies. I'll just brief about the history of additive manufacturing. So you see the first patent in additive manufacturing that was filed in 1860. That is a US patent, and it was published in 1864. That is photo sculpture method to recreate a picture in 3D. That was the first patent. And you see there are actually several other patents or other revolutions, other changes, and they were actually patented. And if you look at this additive manufacturing has come into limelight only at the end of 1980s. Okay, so and that is because of the advancement in processes, advancement in semiconductors. So most of the semiconductors are computers. Sorry, you may get a disturbance as I'm still sitting in the shared room. Please excuse me. So most of the semiconductors development that had taken place in 1980s and 2000. So that's when we actually ended up with a lot of development of hardwares and computers. So that's the reason actually we have additive manufacturing. Though the first patent started in 1860, so it has become more popular in 2000. And you see, this is the first patent. So like you are seeing, this is the contour of the landscape they made by using the wax, right? So and you see this is the sculpture, the first sculpture, which is processed by 3D additive manufacturing. So this is all the very early stage of the development of AM components. And the latest one, what you're seeing is on the right hand side, that was the US patent that was published 1981. So that's what we are currently mostly using, like SLS or SLM or DMLS process. So that patent has origin of this patent basically, or that process has a origin of this patent. So why it is popular now? It is because of computers, and it is because of several availability of softwares and improved automation, and currently we have there are several materials printable. Earlier, maybe even if you take 10 years before, not much materials are printable. So there are very few materials. Currently you see that the library is growing. So now so some 5 years before, printing of copper was difficult. So that's because of reflectivity, high reflectivity, and also it will quickly conduct the heat. So now people have attempted and they made a successful product by using the copper powders. So that has become possible, and it requires huge investment and freedom to operate the patents. So many patents now actually has expired now. So now people have started working on various patents. So this is the reason why additive manufacturing is popular now. Okay, so now you got to know what is the basic difference between conventional and subtractive process, and some bit history about the additive manufacturing process. So now if you look at in India, so both academics, you see almost all IITs and most of the industries and R&D, they started working on additive manufacturing process. So before you get into additive manufacturing process, you all should think when one can switch to additive manufacturing. So you cannot switch to additive manufacturing just because of the fancy word, or just because of you have the liberty of doing additive manufacturing. So you need to meet some certain conditions. So they are so first of all, additive manufacturing, it's not actually replacing, or it can replace the conventional manufacturing process. So rather it can act as a complement. It is a complement to the conventional manufacturing process. Example, you may find some difficulty in handling or manufacturing the components by using conventional methods. So in that case, you can think of additive manufacturing. So this cannot completely replace the conventional process. So it is complementary. That's because of complex and intricate geometry forms that can be manufactured, and simultaneous fabrication of multiple parts in a single assemble. I'll give some examples going forward. And multiple materials and composite materials also possible with additive manufacturing. So I could say that these are all the complements when compared to the conventional manufacturing processes. Now, as I mentioned, you cannot directly switch from unconventional to conventional, conventional manufacturing to unconventional. It has to meet some requirement. So the new process or additive manufacturing process that should add some value into your component. So you need to know what value is being added by adopting the additive manufacturing. Example, I take this component. So this component is something, it looks critical, or it will be difficult, or it will be challenging to manufacture by conventional. So I can think of manufacturing such components by using additive. Okay, so I can actually manufacture this. So here, by additive manufacturing, it added some value. That value is the complexity, right? So it is complex. Then if I have another component, let's say this is the very conventional nut and bolt. Now, can I use additive manufacturing to make such a component? So there is a big question mark. You cannot, because making a nut and bolt, it is conventionally proved. So there are some robust manufacturing methods available. Better you can use those manufacturing processes rather switching to additive manufacturing. So before you choose the manufacturing process, you need to answer these 7 questions. First, what value it adds? And second, cost of the manufacturing, productivity, and technical sustainability. So this all from manufacturing point of view. And one can also look into this, like what is the business opportunity. Say, for example, if you want to get into business, you need to look into what business opportunity it creates, and what is the ROI, that's a return on investment you are going to get on this, and again, business sustainability. So from both manufacturing point of view, from business point of view, you make sure that so you have actually answers to these questions. Then only you can switch from conventional manufacturing process to additive manufacturing process. So basically, what value it adds, what functionality it adds, whether it's manufacturability, right? So, and you cannot choose additive manufacturing just because of the fancy word, or just you have this facility, right? So I'll give some examples. You see here, this is a conventionally processed impeller on the right and top right image, and the top right bottom image is the additively manufactured impeller. And you can see that some value is added by adopting or by using additive manufacturing. So, right. So that is because of, you see here, there are some cooling channels. So you introduce some cooling, you design some cooling channels, and you introduce those cooling channels into the component. So because of the new design, they achieved, there is about 2.5% increase in the efficiency for every 100 degrees Celsius. Okay, so then that's a great achievement. So in this case, you can actually definitely switch from conventional to additive manufacturing, because there is a case here. So the efficiency has increased considerably. This is one such example. I can give another example, is that reduction of weight. So you see here, this is a hinge which is used in Boeing. So Airbus A380. So this is actually having significant weight. So so now you can actually redesign the component such that the weight of the component can be decreased. So so let's say you have some 50 such components, and if you are reducing the weight, you can considerably, you can permit one passenger into the aircraft. Okay, so that saves the money. Okay, so this is another example. So where actually additive manufacturing has been successfully adopted, and they made a successful component with the case studies. Okay, so with that, let me also give so one video wherein they explain the use of additive manufacturing in industry.
And it's really a fantastic engine up to about 800. Let's go to the next one. Next one. So this is the T700.
Are you able to listen to that?
No, Kesavan.
So voice is not coming?
Yeah, it is not coming. Actually, in a share screen, you have an option of at the bottom, like audio also you're supposed to click.
Just a minute. So then I have to stop sharing now.
Sharing, yeah. So now
So don't-
again, share your screen. At the bottom, if you see, there is a one box for like selecting for audio sharing also. If you go to the share screen option, share sound is there like that is there.
While I'm sharing.
No, actually, when you click on share,
Yes.
share sound, yeah.
Yes.
Now it is. Thank you.
In the 1980s,
How about-
you can see it's more complex. It's a more powerful engine than the last.
Subbu, how about
Yeah,
now? Are
now
you
it
able?
is. Yeah. It's audible. Yeah.
Last one we looked at. This is really used primarily for helicopters like the Apache and the Black Hawk. This is basically state of the art today. Now let's go look at what we're going to do tomorrow.
The future.
The future. Yes. All right, so this is the advanced turboprop. And what we've done here is we've taken all of the best technology and learnings from those last two engines, plus everything we've learned on the large commercial engines, and we put it into this.
So what's different about this engine?
Two things that really make this engine different, and that's one, there's extensive use of additive manufacturing.
Oh, okay.
And then the other thing is this has a digital engine control.
What is digital engine control?
The planes that we saw on our ride, basically they all have a hydromechanical control, which means the pilot has to make a decision on everything. So they're independently controlling the propeller, they're controlling the engine.
Right.
So what this does is it simplifies all that into an electronic control,
Oh.
and that frees up the pilot to think about other things, so they can really fly the aircraft instead of flying the engine.
Is this GE's first turboprop engine with additive manufacturing?
It's really the world's first engine with extensive use of additive. Basically, we took 855 parts that would normally exist if we did it conventionally, and condensed that down to just 12 parts. You know, parts that are large, complex assemblies that have to have people assemble those things together, and those parts add weight, they wear out, and they create leakage pads, which robs the performance and efficiency of the engine. So the end result that you have here is a combination of technologies that we've really never used on small engines before.
What do these parts look like?
Okay, so we have some over in the cabinet over here if you want to go take a look.
Yeah, let me see.
So this is a fuel heater. So fuel goes in here, and engine oil goes in here, and heats the fuel.
Now this is one part.
This is one part, that's right.
How many parts would you usually?
So normally this would be about 300.
300 parts.
That's right. Yep.
Is it lightweight?
It is, so it's about half the weight it would normally be.
So this is one part now.
One part.
That.
So yes, that's one quick example. So similarly, I have other videos, but considering the time, I'm not going to play all those videos. But the bottom line here is by using the additive manufacturing, so one can just a minute. Yeah, so this has been implemented in industries, and particularly if you take up take that engine, so 800 components, they're simplified into 12 components. So that simplification is possible just because of additive manufacturing. Particularly if you look at those fuel pumps, so almost like 300 numbers of components as simplified into one component. So this all actually possible because of additive manufacturing. So like this, you can find that there are several examples in industry and the energy sectors and several other examples you can look into in videos. So with that, so let me get into the other topic. That is, what are the steps involved in additive manufacturing? By this time, actually what is additive manufacturing, how one can compare the additive manufacturing with the conventional or subtractive manufacturing processes. Some examples of additive manufacturing are when one can actually choose the additive manufacturing process. So with that, I'll introduce what are the steps involved in additive manufacturing. So you have to start with the design. So you design your component. Then there are so many processes are available, or it has to undergo so many other processes before you actually make it. So it starts with optimization. There are several optimizations. So you have topology optimization, size optimization, shape optimization, all those things. Then once the product is optimized, then you need to convert this into STL file. So it's a .stl file. Once that STL file is created, then you need to actually fix the optimizer. Then you go for support generation and build orientation and all those things. And before you actually go for the print, you make sure the support that is generated is strong enough. So then you go for actually printing your component. So this is the kind of chain of process starting from design to final manufacturing. So I have simplified all those processes into these three. So basically you have your idea, you put your idea into paper, or you convert that into CAD and CAD. So this is your CAD model now. So you need to ensure the CAD model is, or the model that you have created is the optimized. When I say optimized, whether the component is optimized for weight, whether the component is optimized for the surfaces and several other features. So this is where actually design for additive manufacturing comes into picture. So before you put your design into printing, there are some necessary steps to be implemented on the component. Those steps are classified under, or they are put under design for additive manufacturing. So this is what I'm going to explain in the coming slides. So this is just after your idea, just before the printing. You need to just play with some certain rules. It is like get into football, so you have actually some rule of play. So those rules you need to know before you print your component. So once the component is printed, you can use, there are several techniques. You have powder bed, fusion deposition. There are several techniques. Once you print, then it has to go for post-processing. Then you have several post-processings available. I'm not going to talk on all other things. I will be talking only on design of products for additive manufacturing, which is again put under design for additive manufacturing. So let me give actually brief about making a model. So one can make a model. Let's say you have any idea. So let's say you need to make any kind of component. So either you have to make the component from pen and paper. So you just put it on pen and paper, and you develop the component and convert that into 3D by using CAD model. That is one way. That's called forward engineering. That's called forward engineering. Whatever you have generated from your mind, you are converting that into CAD model. That's called forward engineering. So that's what actually shown here. So you have a design idea, then you have to do structural optimization, physical model, digital point cloud, surface fitting. So this is different. So design idea and structural optimization is what actually forward engineering. Okay, this is the conventional. Let's say you have another component, and that component has to be, just a minute. So so that is the first. So design the idea, then your structural optimization, then you are making the CAD. That is called forward engineering. Then you have reverse engineering. What is reverse engineering? So you have a component, which is, let's say that component can be your competitor's component. You want to make 3D printing of that component. In that case, you can do reverse engineering. So the reverse engineering means you have physical model already available. So you have to just create the data cloud, right? That is by using non-contact. You have CMM. So by using CMM, you can actually generate this point cloud, then surface fitting, right? So this is called reverse engineering. So forward engineering is like, this is a CAD model you can directly generate. In reverse engineering, you have to use some kind of CMM. So this is your component. Say, for example, this is your component. You use an appropriate CMM or some scanners. You just scan the component. What you're getting is a complete data cloud. So this is nothing but your 3D model, right? So now you are ready with your 3D model. So what you have to do now, once if you have a 3D model, you need to convert that to 3D model. Basically, you need to convert that into 2D surface, right? So once if you have that, then you can actually convert that into STL file. Then that can be fed into the machine or machine readable file, and that can be printed. So basically, you have CAD. This is, as I said, this CAD model, you can make it either by forward engineering or reverse engineering. Okay, so once the CAD is done, you need to actually convert that into STL file. STL is a stereolithography file. So basically it's a tessellating. You are tessellating the object. You are creating the surface into small triangles, so that it will be easy for you to give it will be easy for assigning the codings. So then what you are doing, you are slicing your component, right? Then slicing is done. Once the slicing is done, then you are making this component into very finite objects. You see, now I can make these small these slices by 2D, right? You see here STL, then I'm slicing, then I'm taking any one slice. So this slice I can make it by so now actually I simplified the problem into CNC. It is now I can use CNC code, G codes, right? I can apply the G code. I can make the tool to move X and Y now, right? So let's say my tool can move like this, left to right and right to left, like this, and it can print one bottom layer, right? Similarly, n plus 1th layer, the second bottom layer can be printed in another layer. So what I'm doing here is from CAD, I'm converting it to STL, then I'm slicing, then each sliced part is now printed, or I have simplified that into so that I can convert into G codes, and my problem is simplified now. So now it'll operate like a CNC machine. Okay, so this is the principle. Now design for additive manufacturing is put in between CAD and STL, right? So here the optimization is required. So that's for design for additive manufacturing, right? So this all then steps involved. So I'm not going to discuss that in detail. And you see here, so this is how it is optimization is done. You have specifications, you fix the specifications. What are the design requirements, strength requirements, AM process limitations, materials? You fix all those things. This all you are fixing the specification. Then you are making the CAD model and you are doing optimization that comes under concept. Then you interpret the results, design evaluation, final design. This all comes under the optimization. Now, I'll give some examples of optimization. So there are actually 4 major classes of optimization. One is structural, size, shape, and topology optimization. So all these optimizations are done to minimize the mass of the component, essentially. So example, if you take the first model, so first models, I know that, right, what is the load acting at the end. If this is the load acting at the end, then I don't have to have actually uniform cross section of the bar. I can reduce this into step. Okay, by doing this stepping, so what I'm doing, so I'm reducing the mass. So this is called, the second step is called the size optimization. The first step is the structural optimization, wherein I'm fixing the cross section D, right? So I'm fixing the minimum D. Then I'm going for the size optimization. And third is shape optimization. I don't have to have this multiple steps. I can have curved surface, right? That's called shape optimization. And finally, topology optimization. So even after having this, you just look at the third image, what I'm with my cursor, I don't have to have actually this kind of feature. So still I have option of reducing the material. So what I'm doing, I'm removing the material at interior. Okay, and wherever there is no load sharing or there is no stresses involved, still I have an option to remove those materials. That's called topology optimization. So structural, I'm fixing the cross section. Size, I'm actually reducing the cross section with the with the length. And the shape, I don't have to have the step, I can have curve. And topology, wherever the material which is not withstanding or sharing the load, I can remove those materials. So this all actually optimization one has to do before you put into print. Okay, so with that concept, I'm introducing the design for additive manufacturing. So before we go to design for additive manufacturing, let us look into design for manufacturing. So design for manufacturing, it gives an idea and it gives basically the rules, methods, and the tools that can assist us for making good decision to make the component. So example, if I'm making any component, I'm starting with the initial design, and I need to always remember what is the functional requirement, what is the functionality of the component. Then there is my first and foremost requirement. Then producibility, handling it, and fitting. So finally, I end up with the optimized design. So this is the conventionally we actually follow. Okay. So now, so anything that we change here, design for our manufacturing, I need to look that my functionality or functional requirement is not affected. Right. So what is the design for additive manufacturing? Versus just how to produce it with additive manufacturing equipment and materials to gain the efficiency. So this is what we need to actually remember for design for additive manufacturing. So the objective here is to maximize the product performance through the design of shapes, size, hierarchical structure, and material compositions subject to capabilities of AM technologies. So this is the objective of DFAM. So we will be doing DFAM, that is a design for additive manufacturing, for these cases. There are 9 cases. I'll explain all those cases with examples. I'll take the first example, that is minimum material that meets the functional specifications. So this is the first example, minimum material. So let's say this is one case study. So I have the component like this. Okay. So it has to just withstand some force acting at this end. So the first design concept I need to apply here is whether is there any scope to minimize or reduce the weight of the component. Okay, so for that I need to do some analysis. Okay, so you can mostly use the analysis, actually FE based analysis. You put all boundary conditions and you see how the load is getting distributed. Now I'm seeing that the load is not fully transferred or fully, I mean some of the regions where the load is not carried. So which means I have an option to reduce the material at that location. So what I'm doing the stress analysis and I'm doing the optimization study. So this optimization study, it gives me an idea which material can be removed, right? Because it gives an idea that this all the material, they do not carry any load. So I can remove those materials and finally end up with the so new design or new product. That's called stress. If I do actually stress analysis on this new component, I'm seeing that so now the stress is equally distributed within all the material. So here I am saving the material. Okay, so this is called design for minimum material that meets the functional specifications. This is a must. We should do this optimization first. So now you see the before and after. So stress is well taken care in the new design. Okay, so this is the design for minimum material. I'll give some examples where in additive manufacturing they implemented it. So what you're saying is this is one bracket, right? So it's a bracket, and this is how conventionally they manufacture. Okay, so this is a heavy component basically. So first, if you apply this design principle in additive manufacturing, that is a design for minimum material, then you have to follow the same step. The step 1, you need to you start FE modeling, or you do actually an FE simulation, and put all the boundary conditions and see where the stress is majorly acting, and what are the components they don't share any stresses or load acting on the component. So you can do that optimization, topology optimization, and wherever you find the load is not shared, you can remove those materials. You see, now you have end up with a completely new design. Now again, you need to actually run this one more simulation, FE simulation. So if you run another FE simulation, you can see that the stress is within the limit of the yield strength of the material. So now this is the valid product, right? So now you are again validating by conducting a suitable analysis. So now this product can be used, right? Now you are printing and finally you are making this product. You see now the initial product is a very heavy bulk, and now with the optimization, the product has become very thin. So by this optimization, you reduced almost 79% in mass, which is huge. Let's say if you're using 10 such loading brackets, so if you're reducing to this much weight, then it gives greater flexibility, right? It saves a lot of money and materials and other things. So this is one optimization which has to be done any component that you put into additive manufacturing. So this is very important optimization. I can use, there are some examples. You see here the same example. This is the conventional design, whereas by introducing the design for minimum material, you see now the bracket has changed. So this component can be manufactured easily by using additive manufacturing. So processing or manufacturing of this component by conventional is difficult. So that's the reason you are originally people in industry, they are using the original component. That's because of you have no option of doing it. Designing is easy, one can design, but manufacturing, when it comes to manufacturing, that would be difficult. So that's the reason they were using the original design. So now with the option of additive manufacturing, so you can play with the design and you can actually make very smart structures. I would say this is the smart structure. So this is the first design for additive manufacturing to minimize the material. So there are several examples which has been successfully used or implemented in additive manufacturing. What you're seeing is it's a head of an engine block. You see this is a conventional, and by implementing the same procedure, the weight almost 76% weight reduction has taken place, right? Which is a huge reduction weight. So like this, you can find several examples in journals or in articles. Okay, so then the second design for additive manufacturing, second principle. I believe you all got the first principle very clear. The second principle is the part consolidation. In the video, what I showed, so they mentioned, so that engine, now they have a new engine, which is designed and manufactured using additive manufacturing, in which 800 parts they reduced into 13 parts, 800 to 13. It's called part consolidation. So more the component you have, more the assembly, right? See, the failure of the component generally that comes from assembly. Say because that's where you have limits, fits, tolerance, leakage is taking place, wear and tear is taking place, and there are several problems when you have more component, more assembly, right? So the moment you reduce the assembly, the part efficiency increases. So another example here, for the part consolidation, see you have, this is the LEAP engine nozzle. Okay, then now the LEAP engine nozzle, it is smartly designed now. You see, it is smartly designed to integrate many components. See, earlier it was made, the component was made with 18 components. 18 components, 18 components. Now with this part consolidation, you can actually simplify this 18 into 1. Okay, so by this simplification, you reduce the weight almost 25%, right? This has become very smart. Okay. The nozzle has become very small and it has become very smart. And the durability lifetime of the nozzle also increased almost 5 times. So the component has become light in weight, and you also made part integration 18 to 1, and the life of the component also increased. So this is called part consolidation. So this is the second principle in design for additive manufacturing, that is part consolidation. And third very important design for additive manufacturing principle is minimum material that meets a manufacturing process specifications. What it means is that you need to always remember in metal additive manufacturing is that you cannot deposit too much material in one direction. You need to take care of it. So what it means is, let's say you have some bulk component. First of all, in additive manufacturing, when you are applying all this concept, you should not make, or you should not end up making a bulk component. It should be smart structure, having thin structure, not bulk structure. If you are designing the bulk component, you will end up depositing a material in one direction. Heavy deposition will take place in one direction, right? So what will happen if I deposit a heavy material in one direction? I'm giving a lot of heat input into that direction. So if I give a lot of heat input, you see here on the right hand side. So if I give a lot of heat input, I may end up with introducing a lot of stresses into the material. So more heat input too. So higher heat input is generally not suggested for structures, particularly if you are making a component for a structural application wherein it has to withstand either static or dynamic loading, so it should be manufactured with a low heat input. Okay, so if you are making a bulk component, so you need to design such that minimum material is positioned in that particular deposition in the particular direction, right? Higher the deposition, higher the heat input, lesser the strength, right? So you should minimize the heat input into the component. So this is the third important principle you should remember. And the fourth is improved function, right? What is improved function is, so example, I'll take this die. So this is a die, basically, it has some cooling channels. Okay, so the purpose of the die is it has to one of the requirement of the die is, so heat has to be dissipated uniformly all across the cross section. Okay, so then you need to make or design the cooling channel such that so heat is dissipated in all the directions uniformly. That is, so by doing that, the functions can be improved. Say, for example, here there are some conformal cooling wherein it is designed such that uniformly heat is removed. Okay, so the idea here is basically if you remove the uniformly all around the product which is getting solidified, so you end up with a similar kind of microstructure in all around. So if in one direction heat removal is higher, in another direction heat removal is lower, then accordingly you end up with a different microstructures. Okay, so you can refer this into TTT curve. So different heating, different cooling rate will end up with a different microstructure. So then you will end up with the different properties. So different directions will have different properties. So then that will limit your function. So to improve the function, so it is suggested to have, in this case, in this application, to have a uniform cooling rate. So then other important is optimized materials. So what I mean by optimized materials, so any component you print in additive manufacturing, it is again challenge, or I would say disadvantage of additive manufacturing. That is, you need to print a component with a support structure. So you are seeing some examples here. So this is your component. Let's say in this case tube is your component, and printing of tube as such is difficult in additive manufacturing. So you need to, because it is overhanging, see, it is overhanging. The moment you construct this layer by layer, so when it comes to this location, higher or top location, the part will collapse. So to avoid that, to minimize that, you need to anchor them. So basically what you are doing some scaffolding, right? Or you are supporting that. So that's the reason it's called supports, right? So you need to anchor from base plate. That's called primary support. If you are anchoring within the structure, it's called secondary support. Okay, so the major problem is these support structures also manufactured from the same material. See, you have a component support structure. Both component support structure are manufactured from same material. Once the component is print, this support structure you will break and you will scrap them. It has no use. This support structure will go as a scrap. So you need to plan something to optimize this. What I mean by optimize here, so you need to design such that you can minimize, or you can deposit, or you can make the support structure with the different material, which is like low cost material or easily dissolvable material. See, what I said initially, you just have to make this with the same material. In that case, you take the component out, you have to hammer them, or you need to cut literally to remove these structures. Okay, so then this all actually post processing, it adds more process after printing. So you choose a material. There are some material like PVA, polyvinyl alcohol. So you just dip the component into the solution. So this support structure will dissolve. It will be dissolved, but that will not dissolve your main structure or main component. So this is called actually optimization, or kind of smart way of handling the structures. Similarly, you see on the right hand side, the right hand side component has more supporting structure than the component, right? So as I mentioned, the support structures are scrap. So in this case, you need to spend more time in removing of the structure. So instead of spending time, you make the component and put it in the solution so that the preferential or selective dissolution will take place, so that only the support structure will dissolve into the solution. So that also can be taken care in the design for additive manufacturing. So that's, yeah. So then the next is residual stress and distortion. This is very, very important as long as you work on metallic materials. So, the one of the procedure I mentioned that you should avoid depositing a material in a single or bulk deposition in one direction, right? So that is one of the DFAM procedure. Then the next is the similar line, minimum residual stress and distortion. What it means, minimum stress and residual stress and distortion. So you all know what is a residual stress. So if not, let me quickly tell you. Residual stresses are logged stress in the material. So, so let's say you do any processing, take any processing like rolling, casting, welding, or any heat treatment, grinding. You apply any processing on a component, those processing will induce some stresses in the material. Those stresses are called logged stresses. So those stresses are generally classified into two: tensile and compressive stresses. So as long as those stresses are compressive, no problem, that will add advantage. If those stresses are tensile, then that will reduce the limiting value of the material. So let's say if the component has 1000 MPa yield stress, and if you have 500 MPa tensile residual stress, then the net is only 500. You can design only for 500 MPa. Okay, so that's the effect of a residual stress. So those residual stresses are formed because of uneven expansion and contraction, and the temperature difference between the previous layer to the present layer. So you need to carefully choose your laser heat input, and the way the laser is interacting with the material, powder or solid, is what determines what sort of residual stress, magnitude of residual stress is introduced. So for example, if you take here, for every layer actually you are giving or you're melting on the surface, you see there is an uneven expansion and contractions. So what I mean by uneven expansion and contraction, one surface is fully in form of liquid, and on the other surface actually it has solid. The moment you remove the heat, so the liquid will try to actually come because solidification is taking place, so it will try to actually come. Since you have different density across the melt pool, so at a different locations you end up with the different strain value, right? So if you look at the net strain, so the net strain will give you some residual stress. Okay, the effect of net strain will not be uniform, so that gives actually residual stress. So for this is due to uneven expansion and contraction while heating and solidification. Okay, so that's what causes the residual stress into the component. So there are many ways to handle it. So that's what. So if you don't take care of the residual stress, what happens? You see here, this all the component failed because of the residual stress. See, you did not apply any external load, right? You did not pull it. So you printed and you kept it on a table, and it failed itself without applying any load. That's because of a residual stress. And this residual stress, as I said, it's because of uneven expansion and contraction or lot of heat input in one direction. So those things will give you such a very high crack, very due to high residual stresses. So how there are many ways to mitigate. So mostly one can actually go for so designing the hatching patterns, right? So you can actually design the hatching pattern such that the heat input is uniformly given, or it is minimized, and actually it is localized. So by selecting appropriate scanning strategy, and you can also choose or such that you avoid mass deposition in one direction. Okay, so this is a way actually to minimize the residual stress and distortion in the component. Then the next is optimized build orientation. Once the part is designed, let's say you have actually designed the part and you have done optimization, then you need to actually put the component for printing now. So before printing, you need to choose which is the optimized direction or optimized orientation to print. So say for example, if this T component, it can be printed by keeping it vertically like this, or at an angle, or inverse, or you can have multiple design. So now one of the important considerations you need to consider here is you choose the orientation such that only minimum amount of support structure is used. Example, among all these things, you can definitely, you should avoid orienting in the first you see the first orientation option that requires a lot of supporting materials, right? You should avoid that. And rest all others are okay because it is not utilizing, or it is not adding too much of supporting structure. So then you need to know some rules, right, for the orientation. Example, if your component is having some angle like this in the structure, if the angle is greater than 45, it doesn't require any support structure. This is the rule. If the angle is greater than 45 degree, this side doesn't require any supporting structure. If it is less than 45, then you need to anchor this side. Okay, so while design itself, you need to take care of it. You need to take care such that you avoid any angle which is less than 45 degree. I'll give other example here. Just a minute. So similarly, there is another example. So the printing of the cone. So how you can actually print the cone? You can keep inverted or vertical or horizontal. So in all these three cases, you have some challenges. So the best possible way is to keep it the second. That is, in this case, vertically up. So you have actually change of cross section. Angle to recoater is easy. Then when it comes to this, an aspect ratio may be difficult. So but here you are actually trading off between many things. So you need to find which is the best optimized build orientation. So considering the several other criteria. So like this, I can give several examples. Then the build orientation, first, as I mentioned, the angle, and the second thing is the number of layers also. So that build orientation, that's also giving the that affects the surface roughness. So this is called a staircase effect. You see, so you cannot avoid it completely. So for example, if I'm creating a surface something like this, as you all know that the component is printed by using small layers, alternative layers. So if I look at the surface, so the surface, I may end up with the step. This step is called the staircase effect, right? So this is what actually contributing for rough surface in additively manufactured component. So to make a smooth surface, you need to reduce the thickness of this layer. So that is the only option you have. So you also actually need to plan such that our orientation such that this staircase effect can be minimized, right? So if you have actually staircase effect, something like this, right? So you may end up with the higher surface roughness, like the steps that you are seeing, right? So this is again build orientation. So there are actually other laser associated parameters. So it's called the exposure strategy. So sometimes we need to expose the upskin or expose upskin. So what I mean by upskin is, see, so the component, see, you see this is the component on the right hand side, you see here. So you see this all the region is called upskin, and this all the region called actually downskin, right? So when you are handling the upskin, so you have to actually handle with some contours. So what it means is that you have to actually have the contour scanning, so such that the surface can be surface roughness can be minimized. So these are all the parameters you can actually handle by using the lasers. So again, so you need to position your component, or you need to design your component such that you have most of the component or is positioned upskin, right? Or so you should have a higher upskin than downskin. You see, this is designed good because you have a lot of upskin than the downskin, because the downskin is the problem basically. Okay. So again, like this, I can give several such examples for orientation. So the next is minimum support structures. So minimum support structure. So example is, if I'm printing this component like this, I need to design such that I'm giving only the minimum support structure. So there are some rules involved. So the rules are like, if I'm having overhanging, if that overhanging is beyond some 10 mm, you need to actually give the support structure. Similarly, for the diameter, if the diameter is about about 8 mm, you need to give the overhanging, right? So there are some conditions that requires supporting structures. So otherwise, if you are taking care of all these things in your design, you don't have to give those supporting structures. So here the objective is to minimize the support structure in your component. So as I mentioned, if you are making any diameter or circular hole, if the circular hole is greater than 8 mm, you need to give the support structure. So while design itself, you consider that you should not go beyond 8 mm. Like you mentioned, 45 or 40 degree is the limit. So you design such that, so this angle is not less than this 40 or 45. And similarly, the overhanging, also you need to take care, right? So this all about to minimize the support structures, right? You see here, if you don't actually design properly, you end up adding more amount of support structure. You see, this is the complete print. After removing the structure, this is your actual component. Okay. So if you don't apply this design for additive manufacturing, you may lose a lot of material, number one, and number two, you will actually end up with a lot of heat input, so that the higher stress in the component. So there are some examples, they are available in literature. You see here, if you don't follow those principles, so what happens, you see here, see it is printed with this is one simple example. This for 50 degree, for 45 degree, for 40 degree, for 35, 30, like this. So what happens, as the angle decreases less than 40, you see that the surface is getting collapsed, right? So what it means, the moment it comes to 40, you need to anchor. So if you don't anchor this region, so definitely your component will collapse. Okay. Similarly, the overhanging, you see here. So if you don't actually give the support for the overhanging, you may end up with the warpage. You see, this is a warping is taking place. Okay. So like this, there are other smart ways. I mean, you need to actually trace all your heat, all your laser and materials input into design for additive manufacturing also. So example, if you take any cross sections, you have hatching, you have contours, you have laser scanning, all those things, all the information should be available in the workflow. So this is all about the design for additive manufacturing. And what you're seeing is, this is the sculpture when you enter IIT Palakkad. This is a sculpture. So we have actually, taken the 3D, like a reverse engineering. We did the reverse engineering on this. So once if we do reverse engineering, we get all the point clouds. Now by using the point clouds, I can actually print the component now, right? So now the challenge here is it has so many angles, so many diameters, so many overhangings. So you need to think, which direction is or which orientation is the right orientation to keep this component for a better quality of print. Okay. So and also you are avoiding support structures. Here you see the blue lines all are supporting structures, right? So by changing the orientation, this blue lines or blue part can be minimized. So you need to optimize that, right? So and again other thing. So you need to position such that you have a large amount of upskin region than the downskin. Okay. So with this, I'm closing my lecture. If you have any questions, I'm happy to take up those questions. Thank you. Hello.
Sorry, Kesavan. Thank you. Thank you very much, Dr. Kesavan. I request the participants to interact with Dr. Kesavan. So, Dr. Kesavan, already there are two questions on the chat box. I will take it up first. After that, I will leave it to the participant. So, number one from Madhi Murugan. He asked about how to know the part is having a residual stress.
Yeah, so Madhi Murugan, actually, we so there are some tools available. So simulation tools. So currently there is the only option I know. So you can say, let's say once you design your component, you use those tools. As an example, you have a Simifact additive. And using the Simifact additive or ANSYS additive also available, you can simulate your printings. So after simulating printings, make sure your net stress in the component is minimum. Right? That is the only way currently we have to check whether the component will have residual stress or not.
Okay, thank you. Yeah, so the next question from Vinay. He asked about, is there any dedicated CAD software for DFA?
So there is no dedicated. There are some materialize magic. Materialize, there is one software. So that's what we also use at IIT Palakkad. So that gives actually best orientation and all whatever design for additive manufacturing principles we talked about. So we can use those software and yes, to answer your question, yes, there are softwares available.
Yeah, so only there are two questions so far. Now I request the participant, please unmute yourself and pose your queries.
Good morning, sir. I do have a question.
Please.
Yes, good morning.
It is you told that the residual stresses is direction oriented. So in what range that is like, if at all, is there any range that we can print in one direction without getting residual stresses? For example, if you are printing in for example, if I want to print 50 mm in the same direction, so is there any range, as I'm saying, that is 50 mm or something like that?
No, I am not completely getting your question. So your question is, let's say if I'm printing a 50 mm.
Yes, sir.
Can you please come again?
In one direction. I just want to print a lengthier part, sir. So up to what range can I expect the residual stresses to be minimum?
Okay, so this is kind of a tricky question again. So you should avoid actually printing a lengthy component in one direction. Okay. So you cannot avoid, you cannot keep one smaller. It's a very high aspect ratio. So you cannot keep on actually building the material in one direction. You should avoid. Otherwise, no, you will end up with the cracks.
Okay, so is there any range of that aspect ratio that I can print without having the residual stresses built up?
Okay. Yeah. So actually, I do not know what is the range, but if you have, if you are reducing the cross section, and you can perform some simulation and see whether you have within any, within the limit. But I do not know any particular number. No, it should be only this cross section at this much range of thickness.
Okay, okay, so I get it, sir.
Okay.
So I do have one more question.
Yeah, please.
So PV or any other material that can be used as support materials. So what about the case in metal additive manufacturing?
In metal additive manufacturing, it's a good question. So in metal additive manufacturing, we don't have option. So
we have to print with the same material, and then we have to do post machining process.
Yes. So in that case, what see, you can play a little smart there. So instead of printing a solid support structure, you can print a porous support structure. You're getting what I mean?
Yes, sir, I get it, sir.
So porous support structure, anyway, a porous structure is supposed to be weak, right? So
yes,
in that way, you can minimize the material. But to answer your question, so both should be from same material.
Yeah. Thank you very much.
Yeah, thank you. Yes.
Okay, there is one question from Punnarasan. You mentioned about optimized parameters should be possible to without post processing. That means the surface finish and machining can be done like that. Yes, asked. In AM process.
Okay, so I'm understanding that can we optimize the optimize the parameters so that we can avoid the post processing?
Kind of possibility. Yes.
Right. So yes. Can we optimize the parameters so that we can see in additive manufacturing, post processing is essential. So there are several post processing. Example. So first is you remove it, and the first post processing is remove the support structure. And the next is you need to most of the component you need to put for heat treatment. I'll tell you why heat treatment is needed. The nature of the process is rapid cooling, so the melting and solidification is taking place so fast. So you end up with a very fine structure with a lot of stress in the component. So you take any component, superalloys or steels or aluminum or any materials, it requires the post heat treatment to be done on this component. So that's the second thing. And third is this component typically will have some kind of a rough surface. So in order to make it smooth, you need to take it for something like polishing, or you need to take it for something like sand blasting or shot blasting, shot peening, something like that. So you cannot completely avoid the post processing just by adopting a suitable processing parameters. One thing with the processing parameter that you can control is or achieve is better surface finish. As I mentioned, by having a minimum layer thickness and also keeping a higher amount of upskin or a large amount of upskin, you can have better surface finish. But otherwise, all other things are not required. So you cannot completely eliminate the post processing. I'll give one more thing also. So if you are making a component for aerospace applications, so that component should undergo hipping also. Hipping is hot isostatic pressing, right? So you need to put your component for heat the component, 3D printed component, and apply pressure in all three directions, so that if at all any minute pores formed due to the process, that will get closed. So it's called hipping. Hipping also required.
Okay, yeah, thank you. And then now one question from Ifam. What he has said, like he's also having the same question. Why is it necessary to have support structure of same material?
Okay. See, the process here is maybe just a minute. Let me see if I have the slide. Yeah, so you are seeing my screen now. You see the process in powder bed, it involves like this. You have a dispenser on the right hand side and you have collector on the left hand side, and the part is being printed here in this platform. So for every layer, so the decoder, which is like blade, it brings one material, brings the powder material from the dispenser to the platform, and it creates one layer. So this is your raw material basically, right? So this is your raw material. So since you have the raw material which is collected for every layer, so you have to print the structure also from the same material. So if so in this I cannot think of adding new material. Okay, so then I have to have one more bin, and when I mix the two different materials in the platform, I may end up with losing the chemical composition of the component. So that is not possible.
Okay, yeah. So then he asked, what about FDM? The same participant.
Okay. In FDM. Okay, in FDM there is that can be planned. So see in FDM. So in FDM again, so if you have different nozzle, so anyway, the hopper or material will be fed into different pool or different nozzles, right? There it can be planned.
Correct. He also has the can't be used two nozzles. Yeah, it is the dual nozzle system. Okay.
Yes, that is possible.
Yeah, there is one question. Maybe I will answer to that question. May we please get the PPT of this presentation? Okay. So regarding this, like anyway, we are recording the lectures. Okay, it will be like uploaded in the Atal website once the program is over. Okay, may I request the participants, maybe if you want, you can download and then refer that recorded video meeting. Okay. Yeah, there is one question from Prithvi Rajan. He asked about if you need to print a tensile coupons along X and Y axis, is it possible to print without warping? What has to be done to mitigate residual stress in such case where the reorientation is not possible?
No. First, you can print. See, for tensile coupons and all, it is not a problem, right? Tensile coupon, it will not. The length will not exceed something like, let's say, 100 or 120 mm. So 100 or 120 mm easily you can print in all three directions. So that's not a problem. So even we are printing tensile coupons in all three directions.
Okay. Yeah.
So I talked about only the bulk components. Let's say the print volume of our machine is about 280, 280, and 320. So such a 280 and 280, and height is 320. So to printing such a big volume or component, there only we need to take care. But the printing of the tensile coupons, you don't have to worry. You can print any direction. It's not a problem.
Okay. Yeah. So I think in chat box there is no more question. Okay, anyway. Yeah, I'll request the participant again. Like, if you have any question, please ask your questions now. I think, yeah. So one question from Danish PB. What you have, the different companies guarantee different mechanical properties for materials. Do we consider this during design?
Definitely, you need to consider these properties for design. So I don't know what you mean with different companies guarantee different mechanical properties. So is it print or component properties or raw material properties?
Yeah.
So that is not sure about. So so raw materials cannot have different properties. So example, if you take titanium. So titanium has unique raw material properties. Maybe print properties may vary.
Yes,
Let's say it can vary print to print. Yeah, Danish.
Yes, it is after printing we get different properties. Some companies say that you should use their material alone. You should not use any other material also, isn't it?
Yeah. So no, it
material
is.
to buy. So
Yeah. No,
yeah,
it is. It is just of. See, I'll tell you before you take up for printing. So only one thing you need to ensure that what is the powder size, powder distribution, right? So mostly it is suggested to use bi-model powders. And so I'll tell you here they play with bit trick. So let's say you're using beam diameter 100 micron. Okay, so 100 micron is so when 100 micron beam is passing on the bed, it should cover a tentative like 4 to 5 particles melting. So that's what
I have
actually.
only FDM, so I have access to only FDM. So I was thinking with respect to that, and actually companies like Stratasys and all, they don't permit other materials to be used. We have
no,
so
yeah. So see,
how
we strictly know.
use other materials.
Right. Yeah.
Okay, what is
So we are no.
are there any standards or something for materials properties when you are designing? So if I design somebody, another person designs with another set of properties.
No, yeah, that's what it cannot be.
Standards or something.
Yeah, it cannot be like that. See, in fact, in our center, we strictly, we don't follow that. So because we know the physical metallurgy, we know the processing concepts, so we know how to handle it. So you don't have to worry about it. So the raw material will have, but one thing you should make sure, that is how the raw material is processed. I'm just again inclined to powder bed fusion process because so that's what actually we experienced. See, the powders can be manufactured by many ways. So people make powders by gas atomization and water atomization, and also by milling and like electrolysis process. There are many ways to manufacture these powders, but those manufacturing processes will have impact on the quality of the component. So as long as, let's say yours is let's say if you are using wire and the processing of the wire is same like your OEM, who is suggesting, then you should not worry about it. So I think you are using wire component, or you are also using powder?
Yes. Wire only, filaments only. So I mean, they are and some machines.
And there are some tracing elements. Yeah. So
no.
Oh, so okay. I'll tell you. You should be extremely careful here. So I'll tell you, there are some tracing elements. Those tracing elements are very dangerous. So example, if you are doing steel, so sulfur, phosphorus are very much dangerous, right? That should be like 0.20 level. So by cheap process, they will not be able to control those tracing elements. So you may end up with a problem, right? So that's what the processing route of the raw material is very important. See, example, steel I can actually manufacture by very cheap way, right? So by conventional, but steel that I'm using for aerospace application, it has to undergo vacuum induction melting, vacuum arc melting, right? So if I introduce vacuum induction melting, vacuum arc melting, so the cost will go like in 10 times, 15 times. So that is the only difference. So as long as you are having the same or equivalent amount of chemical composition, then you don't have to worry about it.
Okay, Kesavan. There is one more question from one participant, Jack Paravesh. So what he asked is, what is the ideal approach to optimize printing parameters for a novel alloy composition?
Okay, so we don't actually optimize this for kind of this novel alloy or super alloy like that. So we basically operate based on the the melting point and what's supposed to be the heat input. So say if for different class of materials we use a different heat input. So like I mentioned, heat input, it composes laser laser power, wattage, and speed at which laser moves, and layer thickness, and overlap. So if I put all this together, I get one number. That number is heat input in terms of joule per mm cube. So that I will fix for the material. That is based on the melting point. So from that number, I can fix what should be my laser speed, what should be the wattage, what should be the penetration, all those things I can fix. I think this is easy to fix. What is the printing parameter?
So that another question from Vijay Kumar. He asked about let me know any possibilities to build a functionally graded material parts using FDM.
Yeah, in FDM it is possible. So in FDM it is very well possible, because there actually you can control the feed material with the time. So whereas in powder bed it is difficult. In powder bed we can have controlled microstructure and controlled porosity. That's what in powder bed. Whereas in FDM you can have graded materials. So different chemical composition with respect to different build position. That is possible.
No more questions so far. Yeah. So participants, like, do you have any question, please? I think.
What are the maintenance procedures for?
Okay. Yeah. So one question from Mohammed Rafiq. What are the maintenance procedure for additive manufactured materials, like for fuel injector or conformal cooling channel, compared to conventionally manufactured material?
Okay. So maintenance procedure.
If I understand correctly, after making the product by any AM process, so how to maintain that? Is there anything specially we have to take care like that? I understand that.
Yeah. That's what I think he meant also.
Yes, sir. Actually, the thing is like for conventional manufactured with, like, we have carburetor, we can open the screws and all that, and we can give some like cleaning of carburetor or things. But in this additive manufactured, is it possible?
Okay.
Like we made a single component.
Okay. So you have integrated component. Is that what you are saying?
Yes, sir. Yes, sir. Yes, sir.
So if it is integrated components, maybe you have to do your regular maintenance. See, if you have something like more complex part which is assembled with a lot of other sub assemblies, so those maybe here you are avoiding interfaces, and those things can be neglected, but according to me you have to do your regular maintenance check.
Okay, sir.
Yeah.
Thank you, sir.
Thank you. Any more questions from participant side? I think no more questions in that case. Once again, I will thank Dr. Kesavan for giving very in-depth knowledge in how to design a part or a component for additive manufacturing process. I hope all of them learned a lot, especially that topology optimization thing. Like yesterday, maybe we discussed with some examples.